So it is mainly about columns. You guys see my screen, right? And you see the column, slide set number 9.
Yes.
It's already posted. We're gonna have 3 slide sets on columns. The first one, it is about something that we call here tight columns. Second is gonna be about spiral. The third one is gonna be about when you have here combined axial load and then some moment on the column. How would you treat a column this way? So first, I want to be sure that you guys know that we're going to be doing only gravity columns in this course. So now we need to understand the difference between gravity columns and seismic columns. Gravity columns mean it's going to be those columns supporting gravity loads. Gravity load means anything related to the weight of the structure itself. Dead load, life load, any equipment weight. This is going to be called here gravity columns. So gravity columns, this is going to be supporting gravity loads. Something is going to be based on the weight. Seismic force resistant columns is going to be those columns in moment frames resisting earthquake forces. We're not going to be going there. We're going to stay with only gravity columns. Seismic columns is going to be more difficult. It's going to be more requirements in the code. We're not going to be going there. So I'm going to show you here different column types, and this is regardless whether it's going to be for gravity or seismic. This type of columns here we call it tight columns. Most likely it's going to be square or a rectangle. And the vertical bars, this is going to be like cross section of the column. And in here you have for rebars, this is going to be the vertical rebars. Also it's called longitudinal bars, if you like. This is going to be like an elevation section of it. And you're going to have ties. The tie is here shown in the plan as one closed tie, but here is going to be like just lines. The other type of columns, we call it the spiral columns. It's going to be like round columns, like round shape. We're going to have the same vertical rebars or longitudinal rebars. And then we're going to have this spiral. The spiral is going to be one piece of rebar. And most likely it's going to be number 3. And it goes like this. It's going to be just one piece. The spacing here is called pitch. And this pitch is usually about 3 inches. So I'm going to give you some like standard numbers that we usually see. This pitch here is going to be about 3 inches, right? When we do spiral columns. The spacing here between ties, this vertical spacing is going to be about 6 inches. So this is going to be about here 6 inches. So that you know the difference between the two type of columns. And this here, this distance is going to be from here to here. Say from here to there, the spacing. Usually call this S. I'm sure that you guys have seen this already in tie spacing in beams when we're doing the shear beam design. This vertical rebars in one of this column, the tight columns, you need to have at least one rebar at each corner. So you see here, this is going to be one of the requirements, right? So I'm going to see here, one vertical rebar at each corner. You cannot just have a column here with only 3 and then you ignore the fourth corner, right? You cannot have it this way. So you need to have a rebar in each corner. In here, you don't have this issue because you don't have corners. But at least you're going to start with 4 rebars or 6 or 8 or 7 or whatever number that you'd like to put there. This column is mainly going to be exposed to axial load. So axial load is going to be coming like this. Same thing for this column, for the spiral column. Exposed to axial load. Now, when you put axial load, now the column wants to open up. Because when you have this high axial force coming to it, it wants to open up, and what's going to keep it in place is going to be these ties. So this axial load is going to be causing lateral strains, and this lateral strains wants to open the concrete up. So if you're going to bring a column like this with no ties at all, and you start to apply vertical load, you're going to see here vertical crack in the middle. It's going to be like a crack like this, which means by applying this vertical force, you're going to have here some tension in the horizontal direction. The way to keep the column together by providing these ties. So now at least we understand the reason that we have ties. This ties here is gonna develop what we call here confinement. So I'm gonna say the reason that we have ties is because of the confinement. So these ties would provide confinement to the concrete. If you have no ties and you start to apply this axial force, you should expect that the failure of the column is gonna happen much earlier, which means the column capacity is gonna be much lower. So this ties here would develop confinement to the concrete, and it's going to increase the axial load capacity of the column. Same thing for the spiral. The spiral here is going to be providing the same confinement, but it's going to be closely spaced. Now, which one do you think is going to be providing more confinement to your column? Is it going to be the spiral column or the tight column?
The spiral?
Yeah, the spiral is going to provide more confinement. Meaning, if I have the same cross-section area of both of these two columns, they are exactly the same. So I'm going to provide here a tight column and a spiral column. Cross-section area here is going to be exact cross-section area here of the concrete column itself. And the vertical reinforcing is going to be the same. If I put here 6 number whatever 7, I'm going to put here all 6 number 7. Don't worry about the column size itself, but this one is, let's say, diameter is going to be a little bit larger than the column dimension in one side, so that the total cross-section area of the concrete here is going to be same as this tight column. So in this case, which one do you think is going to be stronger? Is it the spiral round column or this type of column, the tight column?
The spiral.
Yeah, the spiral. This makes sense. And our reason is because the spiral here itself is going to provide more confinement and is going to be providing additional axial force capacity to the column. And this is recognized in the code. I'm going to show you the difference. Maybe by next time you'll figure out the difference between the two when it comes to equations. Now, is it possible to have like a round column with just ties, with no spiral? Can you build something like this? Is it code recognized? I'm going to say yes. So having tight column not necessarily to be a square or rectangle in shape, like rectangular in shape. It can be also a round column, but with tight. But in this case, you're not going to see the spiral coming up and down like this, and the space is going to be very similar to this. So the term here, tight columns, apply to rectangular, square, and round. It's not just to square. So this one here applies to all shapes of columns. If you have any shape of column, you can have it at tight columns. But in this case, the spacing is going to be like about maybe 6 inches, maybe 5 inches. You can control this, right? It depends on the design and the region that you're designing this column at, because it's going to be based on the code, right? The building code that you're going to be using. I know that we're going to be using ACR, but usually in the building code itself, which is like International Building Code or California Building Code, you're going to see more requirements based on the location. Meaning, if I'm doing here gravity column California, is going to be completely different from, let's say, Minnesota. Because in California building code, we have more requirements. This is going to reduce the spacing here of the time. We're going to show, well, I'm going to show you this very soon today. Now, spiral column, you can have it in round columns, and also you can have it in square columns. And from time to time, you're going to see a square column like this, and the reinforcing is going to be right in the middle, and then you're going to have a spiral like this. And in a case like this, you're going to still design it as a spiral column. Now, the meaning for designing it, for this term here, the meaning of designing it as a spiral column or tight column depends on the equations that you're going to be using, which means you should expect that you're going to have two different sets of equations. One of them is going to be used for columns with ties, the other one column with a spiral. And the spiral here, does it mean it's going to be round? The spiral mean is going to be this spiral or tie that goes around. We call this a spiral actually. We don't call it a tie. This is called a spiral. We have also another type of columns, what we call them here composite columns. This composite columns most likely is going to be like one of these steel pipes, large steel pipe. You're going to fill it with concrete. So the amount of reinforcement that you put there is going to be the outside of the concrete. Here, the reinforcing bar is going to be within the concrete, but here the steel itself is going to be in the outside. Also, if you have a structured steel column and then you encase it in concrete, you can design it as composite column. Now, the axial load capacity in any one of these columns is going to be coming from two components. Same like when we were talking about the shear design. Same when we were talking about just any beam exposed to any bending, right? You're going to have here the concrete component for the strength and also the steel component or the reinforcing component. So in here, cross-section area of the vertical bars besides the cross-section area of the concrete is going to be resisting the axial force. So here when you cut a section, you look at this, you say, I need to figure out the cross-section area of the concrete column and also the cross-section area of the vertical steel rebars. In the spiral column, you'll do exactly the same. You have the cross-section area of the column. It's going to be like this round column. You can figure out this cross-section area. And then you count number of rebars times AB to find out AS. In this case, exactly the same. Cross-section area of the inside of the pipe. And then it's going to be also the cross-section area of this steel shell, which is the cross-section area of the pipe. And you treated it as AS, and it's going to be area of concrete. Same thing here. So it's going to be the same concept. You're going to have some concrete resistance, and also you're going to have some reinforcing resistance. When we're doing beams, the concrete would take all the compression, and the steel is going to be taking the tension. Usually, this is going to be like the concept in our design. But in here, concrete and steel is going to be exposed to compression force. Same thing here, same thing here, same thing here. We have some pictures for tight columns from an actual project. So here's a column, and then we call this dowels. This is gonna be like this rebars is sticking above to be able to pour the concrete slab, and then after that you extend it with the new column. You need to have continuity between the first floor and second floor, for example. This is why you need to extend the bars this way, and then the concrete slab is gonna be coming right here, let's say. Then you're gonna put another set of rebars, vertical rebars, for the column to extend. This gonna be coming from above here and just extend it up, and then put the formwork as the concrete again. This is the way it works. And you see here the ties. You have lots of ties, right? And then you have the vertical rebars. It's gonna be like the formwork that you have for one column. They pour the concrete from the top, vibrate the concrete, and then after that they strip the forms. They take the forms out, and with that you're gonna have this column. Now it's gonna be able already to support vertical loads. All right. How about the spiral columns? How do they look like, and what's gonna be the use of them? Here it's gonna be mostly in buildings, but here this round columns or spiral columns usually used either is gonna be in bridge work, like bridges, or most likely it's gonna be like parking structure. From time to time, if you drive there, if you're walking there, you're gonna see a parking structure with a round column. And look what happened. This is gonna be the spiral, just going throughout the whole thing. Same thing here. Same thing here. And again, you have also the dowels extends above the concrete deck or concrete slab, and then you're gonna bring more rebars and then splice it here. We call this gonna be the splice, because you put this rebar next to that bar. We call this lap splice because you're going to be overlapping the two bars like this. To this length, let's say from here to here is what we call the lap splice of the rebar. This length here. Now think about difference in performance between a tight column and spiral column. You would bring the column, then start to apply vertical load on the column. Let's give you the vertical load, right? And then you measure the vertical strain. So this give you vertical load, vertical strain. The strain in this direction, direction of the load. What happened? You start to apply some load. You're going to see here some strains. And then at certain point, you're going to be reaching here. It's going to be very close from the yield point of the column, which is right about here. Now, after that, you're going to start to do overloading. You put some extra loading above the column. You continue to load it. And look what happened. In the tight column, the ties are going to start to open up. So what does it mean by open up? You see this is what you call here the hook, which is the lock of the tie. When you apply excessive high load in the vertical direction, this tie lock is going to open up. And once it's going to start here to open up, the column strength is going to get reduced, like the way that you're seeing it here. In the spiral column, it's going to continue to support loads because there's no lock here to open. See here? You don't have this hook. You don't have it here. It happens in the top and the bottom, and then you can do a couple of just rounds, couple of rounds of this spiral bar on the top, couple of spiral bar on the bottom. So it's going to be very tight top and bottom. So in here, any one of these ties easily can open. All of this 135-degree hook can open up. And once it's going to start to open up, you're going to be losing the strength of the column. But here, you're going to have here less potential for this spiral to open up because you don't really have any hooks. This is the reason that spiral column is going to be performing higher than tight column. And look at the maximum load value that you can obtain for approach with the spiral column versus a tight column. Tight column is going to be the maximum load. The spiral column, this is going to be the maximum load. So if you have a chance, of course, you're going to do here with a spiral column. But which one do you think is cheaper when it comes to construction?
Tight.
Tight column is going to be cheaper. It's going to be easier. And the spacing of this tie is going to be 6 inches. I guess a person can put his hand here if he is going to be tying the ties together. The wire, they tie this ties to the vertical rebars with wires, but here's going to be tough to keep it in place. And this is going to be very small. It's going to be only 3 inches. And the 3 inches is going to be from the center to center of the spiral itself. Here's going to be the same thing. It's going to be from center to center of the bar itself. So this one here, you're going to have a chance to put your hand and work inside the column, but here's going to be real tough. So it's going to be cheaper. All right, so I guess we need also to have this reduction factor, the phi factor. And in our situation, we don't have any tension in the steel. When you have only axial compression, in axial compression, we don't have any tension in the steel. So we're going to be in this zone. We're going to be in compression controlled failure. We don't have this C over D when you have only axial force. We don't have this tensile strain in the steel. We have only compression steel strain. In this case, I'm going to have here 2 values for the phi factor. If you have a spiral column, your phi factor is going to be 0.75. If you have tight column, it's going to be 0.65. Now I guess we understand the reason of this dashed line. Why do we have it in the code? We have this in the code to address columns or structure members with spirals. Okay, two simple values. I guess when I have a column, it's going to be either 0.65 or 0.75. Simple enough. Here is the equation for type columns for the compressive strength. This equation here says phi Pn. Phi Pn is going to be the axial column strength. It's going to be equal to the following. It says here 0.8. It's like a constant. So let me say I have this constant. And the reason that we have this constant, because if you look at any column, you're going to say this column, I'm sure that there should be some additional moment that comes with the column. You cannot just have pure axial load. Let me go back here to this column elevation, and now let's talk about this. Let's say that you have here in plan, right? And this elevation. Our estimate here that the axial load is going to be right in the middle. But most likely this axial load is going to have some eccentricity because no column is going to have only pure axial force. So I'm going to say most likely this column is going to have some eccentricity, and the eccentricity in this case give it the distance from the center of the column to the point of applied load. I'm going to call this is going to be E, stands for eccentricity. Right? It's going to be the distance from the center of the column to the point of load that you apply on the column. So in plan, I'm going to be saying, okay, let me move this. This is going to be right here. This is going to be the center of the column if you'd like to draw it like as a vertical line here. Again, this is going to be E, and also this is going to be the same as this E, eccentricity here and there. It's going to be the same thing. Now, the moment applied on the column, if I say it here, this is going to be equals to P axial load, and because it's going to be ultimate, it's going to be PU, P sub U. Axial load, factor load. It includes a 1.2 dead plus 1.6 life or 1.4 times dead. It's going to include all of that. At the same time with this PU, I'm going to have also M sub U in this case, which is equal to PU times E, the eccentricity. This little bit of eccentricity, I need to consider it. And with that, it's going to give me additional moment on the column. If this E is going to be small enough so that we can ignore it in our analysis, we call this small eccentricity. So whenever we have a small eccentricity, I can ignore the effect of this moment, and for that, I'm going to be using here this factor of 0.8. So what is the reason that we have this 0.8? This 0.8 accounts for small eccentricity. And in this case, I'm going to say, you know what? Ignore the fact that you may have additional moment, because this moment is going to be small because the amount of eccentricity here is going to be very small. And this is going to be the minimum eccentricity that you can consider whenever you have a column. So now we understand the reason of this 0.8. So the second question about the P factor, why do we have it? I'm going to say this is for the safety of concrete. It's going to be strength reduction factor. How much is this P factor? I'm going to say for type columns, it's going to be 0.65. Where's the source of this piece of information? I'm going to go back here. I'm going to say, because I'm going to have your type column, which means other versus a spiral, is going to be 0.65. It's right here for type columns. Say, okay. Now I have two more components that I need to work with. This one here is going to be about the concrete strength, and this one here is going to be about the steel strength. So I'm going to say, okay, the first one is going to be for the steel strength. Now, which is steel? I'm going to say this is going to be for the vertical rebars. And the first term, which is this term here, is going to be about the concrete strength. Is this a concrete strength in flexure or in shear or in axial load? I'm going to say the whole thing here is going to be about the axial compression. It is not about any tension. It's not about shear. It's not about bending. It's not about flexure. The whole thing here, the entire discussion on axial compression of columns. So this section for this term is going to be about the concrete strength and compression. In this term, steel strength and compression. We're going to be just adding the two values to each other. It's going to be that simple. So actually, this equation could be the simplest equation that maybe you have used so far in concrete design. Simpler than flexure and simpler than shear design. Now let's look at what do we have here for this team. It says here is going to be equal to AST, which means the steel cross-section area, the vertical rebar, not the ties. It's going to be about the vertical rebar cross-section area, multiplied by the yield strength of this rebar, which means we assume that the steel is going to be yielding at the capacity point, and it will. And you don't need to back check this. This is going to be just taken as is. You say AY, FY times AST, cross-section area of the vertical steel. How about the concrete? I'm going to say 0.85 F prime C. And in this case, we need to find out the net concrete area. So this term, AG minus AST, this could be the net concrete area. This is equal to A gross subtracting AST. So you find out the difference between gross concrete section area subtracting the steel cross section area. Also, the code here says you cannot just throw any amount of steel in the column. The ratio between AST to AG, what is AST divided by AG? I'm going to call this to be steel ratio, vertical steel ratio. Let's say in this AST, I want to be sure that AST divided by AG, right, is going to be within certain range. And the range that you have right there is going to be between 1% to 8%. We're going to say 0.01. Some people would write it this way, 1% to 8%. You cannot go lower than this limit, and you cannot go above 8%. 8% is going to be too much. The column is going to be crowded. It's going to be congested with reinforcing. You don't want to do this. And also, you cannot go below 1% of the cross-section area of the column itself. Any questions?
What did the G, the sub G stand for?
A sub G, this is going to be the cross-section area of the column itself.
Okay.
We're going to be going in detail through this. So A sub G is the cross-section area of the column. Let's say a column 12 by 12. Cross-section area is going to be 12 by 12, 144. This net cross-section area is going to be the cross-section area of the column subtracting the cross-section area of the vertical steel. Let me do a quick example here. Let's say I have a column. It's going to be type column. Just quick numerical value. For example, for us, let's say the column size is 12 by 16. I have 6 number 7. My question is, how much is AG? I need your help. How much?
$192 squared.
How much?
192.
Okay. Everybody following us? What does mean by A sub G? Yes? No?
Yes.
Okay, good.
Yes.
About AST, how many rebars? I'm going to say I have 6 rebars. What's the cross-section area for number 7?
0.6.
Okay. How much is this?
3.6.
How much is the steel ratio in this case? It's going to be equal to AST subtracting AG, correct? Divided by AG, excuse me. How much is this?
2%.
0.02?
0.018.
1.8. So I can say it's gonna be like 1.8% if you want to. So this column is okay. Meaning this column satisfies the minimum requirement for the vertical C ratio. And here is the values for this variables, A sub G, AST, and the C ratio. The C ratio usually we call it rho. You know the symbol rho? Rho sub G. I'm gonna show you how it is written in a minute from now. Here is rho. Rho sub G is going to be the C ratio. It's going to be equal to AST divided by AG. And the range for this, as it says here, look at this. Rho sub G, it goes from 1% to 8%. So fine, okay, it's clear. So this equation is really simple. As I said, you have the concrete strength, you add to it the steel strength, you got here Pn, or P sub n. Multiplied by the phi factor, multiply the 0.8, you get the phi Pn. Just to correct myself, if you take the 0.8 multiplied by the concrete strength plus the steel strength, you're going to get here Pn. Multiplied by the phi factor, you get the phi Pn. So 0.8 is part of the Pn. Okay. Now the spacing of ties. We have certain requirements here that we need to be careful about. You see, it says here this S max is going to be 6 inches. So if you have this bar configuration, right, this is going to be maximum 6 inches. Clear spacing. You see this 6 inches? You're going to see it in a few places. This is actually not the tie spacing. This is going to be about the vertical rebar spacing, clear spacing. You don't want them to be more than 6 inches. If this makes sense to you. So what happens if you go more than 6 inches? So I'm going to go here to this case. Or to this case. Let's say to this case. What happened? If the spacing between the vertical bars is going to be more than 6 inches, what would you do? It means that this bar is going to open this way. When you apply this vertical load, the tie is going to be doing this, and your vertical bar is going to start to move out. Right? See what happened? They're going to be pushing this rebar and the tie in this case is not going to be able to brace the bar in place. It cannot keep the bar in place. So in a case like this, once you go here beyond 6 inches, you need to provide this. We call this what? If you like to call it a cross tie. In the ACI, it is used as one word. In the past, it used to be 2 words, like cross and tie. They used to do it this way. Now in the code itself, it's just written as cross tie. Now it's recognized in the ACI. So what is this cross tie? It's going to be this piece of bar that you put there. And why would you put it there? You put it there when the spacing between 2 vertical rebars is going to be more than 6 inches. This is going to be like a code requirement. And with that, once you put this piece, the cross tie, it's going to stop this bar and the tie from opening up. So the question is, what if you didn't do this? I mean, what happened if you did not follow all of these requirements? In a case like this, if you're not following all the code requirements, it means that this equation is not valid anymore. This equation is valid if you do all of that. There's not like, what happened if I'm going to do it like this with more than 6 inches? How much reduction would I get in the trends of the column? There's no code requirement in here or code provision. It just says, if you want to follow this and use this for the trends of the column, you better do everything that we ask you here to do. So once you go here beyond 6 inches, you need to have this cross tie in both direction. It's okay to keep it this way, to keep the column this way, as long as you keep this within 6 inches. In a case like this, you're going to be okay. And in this case, you don't really need to have this cross tie. And then you have more than one configuration if you like. Okay. How about the vertical spacing between ties? Look at the vertical spacing here. How many inches is this from this tie to that tie? Can someone read it for us, roughly?
3 inches.
Like 4 inches, because it starts here at 1/2 at the center, right?
Yes.
And then you start from to say half, and then you have 1, 2, 3, and another half. This is about 4 inches. You see how tight? And look at the other column here. Wow, this is, I guess, closer, isn't it? Just imagine how would the person, you see all of these wires? It's gonna be like the tie wire. And here you see this is gonna be like the cross tie. This is gonna be like the main tie. And this gonna be here the cross tie from both sides because the spacing between the vertical rebars. And just think about the person who's gonna put his hand here to tie all of this and to work in here. Now, how about here? How would you do it? It's gonna be kind of impossible. It's gonna be real tough. The code, the ACI code says the maximum spacing should be the smallest of the following. And then you have 3 requirements here. Number 1 is gonna be equal to 48 times the bar diameter. Which bar diameter is gonna be for the tie itself? Take the tie by diameter, multiply by 48, and this is gonna be the spacing between these two ties. Or you take 16 times the vertical bar diameter. This is to prevent buckling of the vertical rebars. You don't want this rebar to buckle like this, right? You don't want this, the column, to do this, the vertical rebar. So this is why you're gonna put closely spaced ties. And the maximum spacing between ties is gonna be 16 times the longitudinal bar diameter. 1/3 requirement. It says the least column dimension. So for example, in our quick numerical example that I put there, I put the column to be 12 by 16. In this case, what is the least dimension is going to be 12 inches. So the third requirement is going to be 12 inches. In California, we have here a fourth requirement. We have seismic requirements for gravity columns in California in our code. And it says you're going to have here maximum of 6 inches. So when you open the ACI code on some other books, you're going to see this in there, but this is in CPC in California building code. So you're going to limit this. You're going to be adding here a fourth requirement, which is this 6-inch maximum. You're going to say, I have here in California, I'm going to go here to a maximum of 6 inches. In most cases in our design, we're going to be limited by this. So this is going to be controlling our design, the 6-inch. Any questions? No, we're good. Example. All right. This example, it says, find the maximum design axial strength. It says here VPN. See this VPN? Max. This is going to be the maximum strength, axial strength of the column. For the tight column, cross section shown in the figure below. Okay, the column 16 by 16, 1.5 inch cover. Number 3 ties at 16 inch. You can say 16 inch. This is going to be too much, yes, but this is not in California. This is taken here from the textbook. The textbook, you're going to see here 16 inches allowed. If you just follow the 33 requirements, it's going to be okay to go to 16 inch. But if you go to California, you're going to make this 16, you're going to make it 6 inches. Assume a short column, which means no buckling. This is just to avoid the buckling. So all of our work here is going to be for short column. Concrete strength at 28 days is going to be 4,000 psi. And the steel yield strength is going to be 60 KSI for both the steel and the ties. They say here, vertical rebar is going to be 8 number 9. Column 16 by 16. So to find out A sub G is going to be 16 times 16. Number 9 rebar, how much is AS for one rebar, which is A sub B? Someone help me here. Yes?
Square inch.
Yeah. About AST for the column?
8 branches.
Yeah, exactly. How about AG? I'd like to do here also AG. What's the
256.
equation for it? 16 times what?
Mm.
Times 16? This give you how much?
256.
Now, do you think I need the cover for any of my analysis here? Do I need, I mean, did you see the cover getting involved in my design or no? How about the tie size and the spacing? Look at this. Do you see here the cover? Is the cover part of this equation? No, it is not. It doesn't come to this equation. But just give me the complete column section, which is fine. So I'd like here to check the steer ratio. The steer ratio is going to be A times 1. This is going to be AST, right? I just did that, divided by the cross-section area. And it's about 3.1%. This is good because the steer ratio should be between 1% and 8%. How about the column strength? Yeah, I can use this equation, 0.8 times phi. Phi here is going to be 0.65 for 5 columns. Now, where's the concrete strength? I'm going to say here's the concrete strength. Now, let me track it. 0.85 times F prime C for K psi times 256 subtracting 8, the cross-section area of the steel. That was the concrete strength. This is going to be this term here. About the steel is going to be Fy AST. Here's Fy, the 60 times AST is going to be the A. And with that, I have 688 kips. It's going to be that simple. Here's the concrete strength. Concrete column axle strength. Yes, it is, Angel. Simple. How about the ties? I'd like also to check the ties. It says here the maximum is going to be 48 times the tie by diameter. The ties they give it to me, they say is going to be 3/8 of an inch, number 3. So 3/8 of an inch is going to be number 3. This is going to be the bar diameter. So I'm going to say this part here is going to be dB. dB, which means the bar diameter, times 48 is going to be 18 inch. 16 times longitudinal bar diameter. The bar diameter, the vertical one, is number 9. Diameter is 1 1/8 of an inch. To get to the actual size from the table, it's going to be 1.128. So also it's going to be 18 inch for the second requirement. Third requirement is going to say here the least column dimension. The column is 16 by 16 anyway, so it's going to be 16 inch. So the tie spacing given to me here as 16 inch for the spacing is good, as long as you don't do it in California. If you want to do it in California, it's going to be 6 inches. So this is going to be okay, but I'm going to say here, not in California, according to ACI only. Once you get to California, you're going to make it 6 inches. Now, do we need to have cross ties? You remember this cross ties? It says here, if the spacing is going to be less than 6 inches, you don't need them between two vertical rebars. If it's going to be more than 6 inches, you need to put them. That was a cross tie requirement. So let me check. It says here the clear spacing or the clear distance. Now I understand why I need the cover. So the cover is not going to be in the equation for the axis strength, but it's going to be for the spacing between two vertical rebars. Let's say, okay, let me figure this out. Yes, here 16 inch, subtracting 1.5 inch from each side, subtracting number 3, which means 3/8 of an inch, 1 from each side, subtracting. Now with that, I have the distance from the outside of the vertical rebar to the outside of this vertical rebar. Now subtract 3 times 1 1/8 of an inch, and then at the end you divide by 2 because you have here 2 spaces. Any questions with that? Let me see the numbers. 16 subtracting 2 times, what is that number here? What is that for? See, this is going to be for what? For the cover, clear cover. Two times 3/8 of an inch. Can someone help me and tell me what does that account for? 2 times 3/8 of an inch. What is that for?
Is that the ties?
The ties.
Yeah. What is this 3 times 1 1/8 of an inch? What is that? Okay, say this is gonna be for the vertical rebar, right? It's gonna be 3 number 9. 3 times the diameter. And then at the end, why would you divide by 2? Why not divide by 3? Can someone help me with that? What's the reason of this? 2 what? Spaces. What are these 2 spaces? Let me confirm this again. I have 2 spaces. Here's the first. And here's the second. Now, if the clear distance here is going to be more than 6 inches, I need to put cross ties. I'm going to tell them, I cannot really find out this axial compression strength. Why? Because you're not following the code requirement when it comes to steel detailing. We did the analysis, it's 4.4 inches, less than 6 inches. So we're good. Means this compression force strength or compression strength is okay, because we followed all the details when it comes to the tie spacing, right? Vertical spacing and the cross tie requirement. Any questions?
Why are we subtracting it from 16 again? I'm sorry.
Why do you subtract this from 16? Okay, let me go through this again. We're trying to figure out this clear spacing, right? So how do we do this? We take 16 inch, the total distance. We subtract first the cover from here to there and from here to there, right? And what's next? We subtract the tie size, which means this little distance, 3/8 inch from here and 3/8 inch from here. Do you see my screen well?
Yes.
Okay. And then what else we should subtract is going to be the diameter of this 3 vertical rebars. So the equation says it's going to be 16 minus 2 times 1.5 minus 2 times 3/8 inch minus 3 times 1 1/8 inch. At the end, you divide by 2. So you find out the clear spacing between 2 vertical rebars. If this is going to be more than 6 inches, you need to have cross tie, like what the requirement here says. If no, yeah, go ahead.
So we're just looking at the concrete. We want to see if we have, it's just for the concrete, right? That's why we're subtracting all of the steel.
Yeah, because you'd like to see the clear distance or spacing from a column from this rebar to this rebar.
Okay, thank you.
No problem. All right, next example. You have 24-inch by 24-inch concrete column. I see here that you have cross ties in all directions. I see the column at typical clear distance is going to be 1.5 inch. Okay. 24 by 24, 5,000 psi concrete. It says determine the maximum column axial load capacities for the column based on the code range of vertical reinforcement ratio. So I need to explain to you why I'm doing this. What is this code range of vertical ratio? The vertical steel ratio is what? Anyone remembers? Anyone knows? From 1% to what? Yeah?
1 to 8.
To 8%. In many cases that you have a building that you're working the design of this building, right? And then the architect is going to come and say, we'd like to minimize the column size. We don't want to go very big. So you're limited with the column size. So the thing that you can change or work with is going to be the amount of reinforcing bars. You put more reinforcing bars, you gain higher strength, right? This is the way it works. So for each column size, you'd like to know what is the range of the capacity. What is going to be, like if you're going to go here as a code minimum reinforcement, what axis strength you're going to be gaining. And if you're going to go here with the maximum steel ratio, how much would you be gaining out of this column in terms of strength? You don't want to go to 8%. 8% is going to be too much. It's going to be very tough to build it. And people on the side is going to be complaining, right? So you don't want to go to 8%. Maybe like keep it 3% for the maximum, maybe 4% max. So this is based on actual practice. You don't really push it to 8%. So usually when you have the column size, you'd like to know what range can I use this column for? And then based on this, I can decide how much reinforcing based on going to be on the demand given to me. The main meaning is going to be P sub U in this case. That's okay. How much is this A sub G? Gross section area of the column? This gross section area is going to be 576 square inches. Now I have two cases. The first case, when I have only 1%, it's going to be the code manual C ratio. You see this? This is going to be the first case. How about the second case when I go here to 8%? It's okay. Let me try the first case. 1%. I will try number 8. Why do I need 8 rebars? Because in a case like this, you cannot have less than 8 rebars. Look at this, 24 by 24 inch. You cannot have less than this number of rebars. You're going to have 1 rebar at each corner and 1 rebar is going to be in the middle. Otherwise, the distance here is going to be big, right? So you're going to be going here with 8 rebars. You can pick, let's say, if you pick here number 8, this AS is going to be 6.32. How about if I pick number 7? How much this is going to be, in your opinion? How much? 8 times 0.6 is how much?
4.8.
4.8. Is this less than or more than 1%?
More than.
More? Can I use 4.8? Based on this, the minimum is going to be for 1%, it's going to be 0.56 or 0.58 or 0.57 square inches, right? So I cannot use really 8 number 7. So I'm going to start here with 8 number 8. 8 number 8 is going to get me still of 6.32. Divide this by the cross section area. I'm going to be at 1.1%. So I can really get to 1% exactly. You cannot get to it because the rebar size, because number of rebars that you need to use, right? So you cannot get it to exactly 1%. So 1.1 is good. This is going to be the closest to 1%. I'm going to say this is going to be the minimum I can put in terms of rebars. From the equation. Now, I guess you guys are aware of this equation, but let's go through it again. This 0.65 is going to be your phi factor, right? I'm going to say phi factor. 0.8 is your constant for the small eccentricity. Perfect. 0.85 F prime C. What is this F prime C? 5 case sign. Concrete strength. 576 is going to be A gross. Subtracting AS. You see this AS? This is going to be the concrete strength term. It's going to be the steel strength. 60 times 6.32. Total of 1456. So for this column, if you like to start with 1%, you're going to be at 1456 kips over capacity that you can compare it to your actual demand, P sub U given to you. And then you can decide if this is going to be a good design or not. Okay, let me try here the 8%. I'd like to get here to 8%. The problem is going to be how many rebars can you fit in here? And what arrangement would you do? So in this case, you say, based on experience, I can put 1 rebar here. I can put another rebar right next to it, like this, right? And another rebar here. Now, how many rebars can you fit? I'm gonna say 3 at each corner, right? Can put them, keep on adding rebars, right? We call this gonna be bundle rebar. How many rebars that you guys have now? Did someone help?
16.
16. Can I add more? How can I add more rebars? Can I do this? Just bundle this rebars. How many you have now?
20.
All right. Can I do something like this here? See, I'm just showing you here what's gonna be the layout of the rebars, right? Because you'd like to add more rebars. How many rebars now?
24.
24. Can I add 4 more? I say, yeah, well, you can do this. I know it's gonna be tight. You have here plenty of rebars. This is the best we can do. Now, how many?
28.
Now, do you want to add more rebars? You have a chance to add 1 rebar here, but this is gonna be beyond the 8% if you do it this way. I'm gonna go here to the largest rebar that I can use, number 11. And with that, I'm gonna be using 28 number 11. Cross-section area is gonna be 43. 8% is gonna be 46. The actual rho sub J, which means vertical reinforcement ratio, is gonna be equal to about 7.6. This is the worst case. I cannot go beyond this. Now let me try my equation again. 0.65 and the 0.8, this is gonna be the small eccentricity factor and the phi factor. This term here for the concrete strength, and this term here is gonna be for the steel strength. Total of 2,540 kips. Now this is gonna be the maximum value that you can get out of 24 by 24 when you put nearly 8%. It's gonna be roughly 2540 kips. And if you like to go here with the minimum steel, you're gonna go here to 1456, or let's say 1460 kips. So now you know the range. You know that this column is valid between 1460 to 2540 kips. If your load demand is gonna be within this range, you're good. I can use this column section and just change the amount of reinforcement that I have there. Otherwise, this column is not good. Let's say that I have bigger demand than 2540. In this case, I'm gonna say 24 by 24, it's not gonna work. I need to change the column size. Any questions?
Can you repeat that again? What the solution is? So
The solution at the end of the day, I'm gonna put it here. I'm gonna say this column is good for this range. What range? Range of loads, right? Axial capacity. If your P sub U is between what? What was the value again? 1456. So I'm gonna say here 1456. 2. What is the upper bound? You see this one? 2539 kips. What's gonna happen? This column is good for this range. Otherwise, change the column size. Does it make sense? You understand the reason of this exercise? I'd like to know if this column size is gonna be okay and for what range of vertical loads. Any questions? We're good?
Would we be able to add more columns if we add them different size, or is it right now okay for us?
You can change the column size. This is gonna be one way. You can change the column size. But if you change the rebar size, would that change the fact that I went here to the maximum? I went to nearly 8%. So even if you change here the rebar size itself, I mean, I went to the maximum. I'm about 8%. You cannot add more rebars. And I went with nearly 1.1%, which is about 1%. So this gave you my range for the axial strength.
Thank you.
No problem. If you have larger demand on the column, then you're gonna say, well, I need to change the column size, or maybe I need to go to stronger concrete. Because part of this equation, if you see here, F prime C, correct? Up to 5,000 psi, the concrete cost is gonna be okay, manageable. Once you go to 8,000, it's gonna be just too high, and the cost of concrete is gonna go up. So in a case like this, you may be asking, isn't it easier if I'm gonna go here to 24-inch by 36-inch column? Now I can play with the column size because I have here few parameters. I have the concrete strength, I have the column dimensions or column size, I have the amount of rebars. So what I have done here, I kept the threads the same, I kept the column size the same, and I changed here, I played with the amount of reinforcement that I can put there.
We can
You
also
still have,
do steel strength, right?
what's that?
Steel strength, we can also increase it, right?
Yeah, but it's gonna be kind of tough to find. To find different grade of steel like 75, this is not easy.
Okay.
But yes, if someone says grade 75 is available, you're gonna say, okay, let me try grade 75. But most likely this is gonna be kind of tough to find. All right, I'll let you go unless you have questions. So stay around and ask me. And to ADS, you can use in the rebar size. Satisfy the AS max. This is correct.
So do we not account for the area of the steel in like compressive reinforcement in our beams because it's so much smaller?
No, we account for it. Look at this. It's right here.
No, I mean in our beams, right? When we had compressive reinforcement.
Oh
we
yeah,
didn't-
because we ignore the steel in the top, right? Generally speaking, we try to ignore it in the beginning. And usually the amount of steel that you put there is not gonna be like this amount of steel. You don't add number 8 in compression, right?
Right, yeah.
It's gonna be maybe a couple of rebars number, like for example, you say 2 number 5 is gonna be 0.62 versus 6-inch. So
Yeah,
it's gonna be maybe 1/10 of that, so you can just ignore it.
I see. Okay.
All right, you guys have a good night.
Oh, one last question.